Hello everyone, and welcome to our very last lesson, 9.7, on solving right triangles from chapter 9. So solving right triangles is just going to be where we put everything together. So it says to solve for a right triangle means to find all unknown side lengths and angle measures. So you should finish with a total of 3 known sides and 3 known angle measures whenever the whole triangle is solved. So there are going to be 2 situations which allow you to solve for the rest of the right triangle. The first situation is when you're presented with 2 side lengths. The second situation is when you're presented with 1 side length and 1 acute angle measure. If you don't have at least at a minimum that amount of information, we cannot solve for the rest of the right triangle. So let's think about what is a right triangle. It contains a right angle by definition. And so if we have nothing but the right angle, there's no way to find any sides and there's no way to find any angles. But if we're given at least 2 sides, we can complete the rest, meaning we can find the third side and the other 2 angles. And if we're given 1 side length and 1 acute angle, then we can find the rest as well. So we'll see that pop up. Let me give you an example. So on this very first one, it says solve for all the unknown sides and all of the angles for each problem. This is important. We were practicing this a lot in my class this year. Round the side lengths to the nearest tenth, but we're going to round the angles to the nearest degree. So we already have one of the angles, it's 90. And then we already have 2 sides. I have 2 sides. So we're going to be able to find the third side and the 2 acute angles because of the information that I'm given in this triangle. So this is an example that matches, like if I were to color code this matches where it's given 2 side lengths. So this would be a pink star, 2 side lengths. Okay, so let's see what we can do. I am a big fan of the Pythagorean theorem, a squared plus b squared equals c squared. So the first thing I'm going to do is I'm going to find side C. I'm going to put a C above that, side DE, by doing the Pythagorean theorem. I already have 2 of the 3. I might as well go ahead and plug it into a squared plus b squared equals c squared. So we'll start with a theorem that works for right triangles and allows us to find missing sides. So that's going to be 20 squared plus 21 squared equals c squared. And so what happens when we type that in, 20 squared plus 21 squared is 841. That's what c squared is equal to. So we're going to take the square root of both sides. And I believe that happens to be a perfect square. It is. So that is going to have a length of 29. The first thing you're going to do is ask yourself, does that make sense as an answer? So go put it in the picture. Is the hypotenuse of 29 bigger than both of the legs, 20 and 21? Yes, it is. Okay, so even if I've made a mistake, at least it is a logical answer. Okay. So now let's look at finding the angles. How do I find angles in a right triangle when I have side lengths? I'm going to be using some inverse trig. So to find angle E, which I'm going to call theta, I'm going to use the known pieces. I know that I have all 3 and I could use any of the sine, cosine, or tangent that I want since I have all 3 sides there, but I'm going to use the ones that are known and that were given to me because I know for sure that those are accurate. So 20 falls opposite the theta. The 21 falls adjacent to the theta. So I'm going to use inverse tangent. And that way, if I happen to make a mistake on finding the hypotenuse, it doesn't burn me twice, okay? So we're going to do the inverse tangent of 20 over 21, opposite over adjacent. And so when you type that in, inverse tangent of 20 divided by 21, you get 43.6, so we're going to round that to about 44 degrees because it wants it to the nearest whole number. So what is angle E? Angle E is going to be about 44 degrees, okay? Now at this point, this last part is really easy to find this other side, or this other angle right here, this dot, angle D. I just get to do 180 as the total, minus 90, minus, what did I just find, 44? Minus 44, it's going to be the complement of 44, so 180 minus 90 minus 44, or the complement of 44 is going to be 46, I believe, 46 degrees. So that goes ahead and gives me that rounded whole number. I do want to show you, though, that we could have used trig from this angle and done opposite over adjacent. So had I used trig, it would have been this angle is equal to inverse tangent of 21 over 20. Now when I type that in, I am going to get a decimal, 21 over 20, which is 46.3, but that would round down to be 46 degrees. So I get the same thing whether I use trig or whether I use the triangle angle sum theorem. So we have found all the sides. We have all the sides now, and we have all the angles now. Okay? All right, so here's an example of the green star, where we're given 1 side length and 1 acute angle measure. So the easiest thing to do in this situation is I already have 2 of the 3 angles. Let's go ahead and find the third angle using that third angle's, that triangle angle sum theorem. I know that these should have a sum of 180. So if I take 180 and I subtract off what I spent at the right angle, 90, and what I spent at the other acute angle, that's going to give me my remainder amount of 65 degrees for this other angle. So this star angle right here is going to be 65 degrees. Okay, so now we have all three angles. We just need to find the other sides. So the first thing I'm gonna do is say, okay, I've got a 25-degree angle. My known thing that's there is a hypotenuse. I wanna find an unknown, so maybe I wanna find HJ first. I wanna put an X there to show I'm looking for it, because I need to figure out what that relationship is to X. So from the 25-degree given angle, X is opposite and 13 is hypotenuse. So I'm gonna use normal trig. I'm gonna use sine of 25 degrees equals opposite over hypotenuse, which is X over 13. Again, we put this over 1 to cross multiply, and thankfully X is already going to be by itself on one side. X is going to be equal to 13 times the sine of 25. So let's see what we get when we type that in. 13 times the sine of 25 should be about 5.5 when we round it. It says to round these to the nearest tenth. So about 5.5. So I called that my X. That's about 5.5. And I'm going to show that it's rounded. Okay? All right. So at this point, this does make sense as an answer. Always plug that back in and check it. Check yourself before you wreck yourself. 5.5 is a leg, which is smaller than the hypotenuse of 13, which is good. At this point, you can go one of two ways. You can either use trig again and use trig to solve for y. I'm going to put a variable there. And so I'm going to do that way, and I'm also going to show you get the same thing with Pythagorean theorem. So from 25 degrees, my hypotenuse is there, and my y is my adjacent. So what goes with adjacent and hypotenuse, if I'm just looking to solve for that purple piece, that's going to be cosine. So the cosine of 25 degrees equals adjacent, which is y, over hypotenuse, which is 13. Why did I do that instead of working with the 5.5 that I just found? Because the 13 was given, whereas I could have made a mistake on the 5.5. So that's just working smarter, not harder. So y is going to be equal to 13 times the cosine of 25. And when I do that, 13 times cosine of 25, I get about 11.8. So this is about 11.8. Does that make sense as an answer? Is that less than the hypotenuse of 13? It is. And so that's going to be about 11.8. Had you used Pythagorean theorem instead to find the purple piece, here's what would have happened. A squared plus b squared equals c squared. Of course, my c is my hypotenuse, so that's going to be y squared plus 5.5 squared equals 13 squared. And so what you're going to end up typing in your calculator is 13 squared minus 5.5 squared. And that is going to give me 138.75, and that's what c squared is. So when I take the square root of that, I get 11.77, which rounds up to 11.8. So this is our trig approach. This is with trig. You get 11.8. This is our, I'm sorry, that's not trig. Hold on. That's Pythagorean theorem. Here we go. This is our Pythagorean theorem approach, our pi theorem. We got 11.8, and from our trig approach, we got 11.8. So you choose how you want to approach it. So there's one of each kind. And so you will practice that on the back. And the only other thing that's going to come up is being given, determine which of the acute angles has the given trigonometric ratio. That's fun to say, trigonometric ratio. So they're going to give us a trig ratio, and they want to determine which angle, which of the two acute angles has that trig ratio. Then determine if there are any other trig ratios that will result in the same ratio, okay? So the cosine of the angle is 4 over 5. That's what's given. Cosine of the angle is 4 over 5. So I'm going to write that out because it kind of helps me out. Cosine of theta, whatever it is, should be equal to 4 over 5, okay? So what we're looking for is what has in the ratio of an adjacent to the hypotenuse being 4 to 5. So obviously this is a ratio, so it's been reduced. Possibly has been reduced. And so we're just going to check both acute angles. I'm going to check the yellow angle, and then I'm going to check the blue angle if the yellow angle does not work. Okay? And so you'll get good at this as you kind of look through it and see which one to try first. But let's just say we had no idea. We're just going to start with a star. What is the cosine of angle A? So cosine at A. Cosine at A would be adjacent 6 over 10. Well, we need to reduce that. What is 6 over 10 reduced to? 6 over 10 is going to reduce to 3 over 5. That's 3 over 5, okay? So that is not what I was looking for. So now we're going to try the other one, so we know it's not A. So now we're going to try angle C, cosine of C. Cosine of C is going to be equal to adjacent over hypotenuse, 8 over 10. What is 8 over 10 reduced to? 8 over 10 reduces to 4 over 5. So which one actually matched? C is going to be what that one is, okay? So the angle that had that one is going to be angle C. Angle C. I'm going to change this star so it doesn't look the same. I'm going to change that to a heart. So my heart angle was the one that had the cosine of 4/5. My star angle had a cosine of 3/5. So angle C is going to be my answer that has that ratio. So if angle C has a cosine ratio of 4/5, who also is going to have a cosine ratio of that? Well, remember that when we set this up, we said going from A, we had the sine of A was a certain thing. We had cosine of B, cosine of A, and then we had tangent of A. So all three functions were there. And then we said, okay, coming from the other side, that would be from angle C, we had the sine of C, we had the cosine of C, and we had the tangent of C. And we learned the relationship that the sine of A is always going to be the same as the cosine of C, those two acute angles. The cosine of A is always going to be the same as the sine of C, and the tangent is going to be A over B, so it's flipped, of the tangent of C, which is going to be B over A. Okay, that's as far as a fraction goes. Let me use different letters for that, just because we're working with A's, B's, and C's. So if let's just say we called the tangent of A is equal to x over y, the tangent from the other acute angle is going to be y over x. So it's just that fraction, and it's the inverse of that. Okay, so what else is going to be the same as let's see, color code it. What else is going to be the same as angle C? We said that is the cosine of C. Who's the same as the cosine of C? Cosine of C is going to be the same as the sine of A. Sine of A. Sine of A. And we can check that. Let's look at it. That pattern helps you find this. The sine of A from angle A, opposite over hypotenuse, would also be 8 over 10. So we know that 8 over 10 reduces to 4/5. Okay? But just learning that pattern helps a lot. All right, let's do this again. Now, this one doesn't give me a fraction. This one gives me a decimal, so I'm actually going to have to divide these out. They say that the sine of whatever my angle is, theta, is going to be equal to 0.96 when I divide it out. So let's color code this. I have two acute angles. One's in blue. I'm going to do the other one in yellow. Which one has a sine of 0.96? So let's just start by calculating. The yellow one, let's go to the yellow one. So from angle C, my sine, the sine of C, is going to be equal to opposite over hypotenuse. So what is my opposite over my hypotenuse? That's going to be 7 over 25. So let's see if 7 over 25 is going to be, obviously it's not going to be 0.96, but let's type it in just to check. 7 over 25 is 0.28, 0.28. So we know it's not that sine of C. So it must be the sine of A, but let's check it. Sine of A is going to be equal to its opposite over its hypotenuse. What is its opposite? 24. What is its hypotenuse? 25. That seems much more promising. 24 divided by 25 is going to give me a decimal of 0.96. So sine of theta equals 0.96, sine of A equals 0.96. So my answer is going to be angle A. That's the one that had that ratio. So who's going to be the same as the sine of angle A? Sine of angle A is going to match the cosine of C. So we're going to go ahead and fill that in. It's going to be the cosine of C. All right, your assignment is on the back, and we will be doing that in class for the people that are here.